Now that we understand how charges are affected by electric fields and magnetic fields, we can understand a velocity selector. Charge plates here establishing an electric field, in this case up. A positive particle moving to the right is deflected, pushed upward by the electric field. The magnetic field coming out of the page, put your fingers out of the page, put your thumb to the right. Your palm is pointing down. It deflects that particle down. These effects are oppositely directed, and if they're chosen just right, they should equal, cancel each other out. So let's mix up the field configuration a little. Electric field, magnetic field. Electric field now is going down. Magnetic field is going in. Let's place a charged particle. Impose that particle into this field combination at some velocity v. Now the goal is to get it to go straight through. Now it will go straight through if the proper conditions exist, namely that these two effects cancel. So how does that look? Well, the electric field will push down on it, so we have a QE force. The magnetic field, fingers into the screen, thumb to the right, palm is up. So that pushes up on the charged particle with a QVB force. To pass straight through, those have to be equal. Q's go away, and we have velocity equals E over B. That's amazingly simple. A wonderful result. The velocity that's selected for the particle to pass straight through these oppositely interacting electric and magnetic fields on the particle is just the ratio of E over B. That is the velocity of the particle. Notice what it's not dependent on, which is kind of surprising, the charge and the mass. So charge and mass are both independent. Find that ratio, and you've got your velocity. So using the velocity selector, we have a famous experiment known as the Thompson experiment, J.J. Thompson. In the 1900s, he was born in the mid-1800s. So there he is with his apparati, kind of like this in schematic form here. So here's the velocity selector. We're sending a particular series of charged particles that have been accelerated across the potential difference. So here's what's going on. We have this voltage across here. And let's say we have a negative charge. It could be an electron. It could be a bunch of elementary charges, or a particular ionization state of a particle. In any case, the velocity as it's accelerated toward off the negative toward positive here, these are slits. It has a certain amount of work done to it. And then it goes through the velocity selector. Now the work on the electron from the electric field is going to give it a velocity delta K. There's going to be a change in its kinetic energy. All right, so the work is Q times V. Potential difference times charge, so that's delta K. Now the Q might just be elementary charge. If you can get a single elementary charge, say for sake of simplicity now, this is just an electron. An electron times the voltage is equal to 1/2 mv squared. So EV is 1/2 mv squared. Solving for V, square root of 2EV over m. Now, the adjustments of the parameters here in the selector to enable this charged particle to come through. The kinetic energy is 1/2 mv squared, but we know that the velocity is E over m, E over B, electric field over the magnetic field. So that ratio is this ratio. So we can do the algebra on that, square both sides, and get E over m out of this. E over m, E squared over 2VB squared. And what Thompson discovered is that no matter what state of charge the particle was in, what the charge was, and the mass, and whatever the mass is, maybe not knowing particularly what the mass is, but adjusting these adjustable parameters, the voltage, the magnetic field, the electric field, this ratio would always equal this. And so with doing enough experimentation, he discovered the discrete nature of the charge. And so this E over M, he didn't know what the particular value of M was, or E for that matter, but because he knew this ratio, he could always discover the ratio and saw its discrete nature down to a single elementary charge divided by its mass. He was credited with discovering the electron, even though the particulars, the mass and charge, were actually discovered by Millikan about 15 years later. Okay, now we can put these ideas together to understand a mass spectrometer, which is basically a device that is able to accelerate charged particles and then put them through an additional magnetic field that has a certain force acting on those particles. And if they're more massive, they will have more inertia and be curved less in that magnetic field. Less massive particles, greater acceleration to curve them more because of their smaller mass. And the detector plate picks them up at certain locations, and the mass can be calibrated from that. So let's look at the details again. So here's the part that accelerates the charge, and we're going to have a positive charge here going through the slits with a known amount of work done to it based on this V and the Q. So here we have our electric field and magnetic field to select the particles. The velocity that the ones coming through straight will have is E over B again. But now those particles, those ions, enter a new magnetic field B prime. This one I have coming out of the page. So stick your fingers out of the page. The velocity is to the right. Put your thumb to the right. Your palm points down. And so it curves down and hits the detector plate. Okay, and there's some radius. There's some radius R. We'll call the mass M1. Well, when the ion enters that secondary magnetic field, we can say the QVB force. The QVB force acting on it is the centripetal force, mv squared over r. One of the v's goes away there. We can calculate r, mv over qb prime. And so now v is E over B. So E over B. That's the original electric field and magnetic field of the selector. From this, we can solve for the mass. The mass is Q, B, B prime, R over E. All very quantifiable. We know what they are. We can adjust them at will as necessary. But the conditions being just right with the selector, that particular mass entering this magnetic field will curve a certain amount, and it's all clearly listed there. What that does is enables the determination of different masses. Why is that important? The mass of different isotopes. For instance, radioactive decay will produce in a sample a certain percentage of isotopes of one mass versus the other. So the sample can be measured and the relative quantities of different masses detected, and thus the age of the sample can be determined based on the half-life. So we have that new mass, a larger mass, say, just having a larger radius, and therefore the mass. So let's do a Thompson experiment here. We have some known values, a 150 volt accelerating source. The electric field is 6 millinewtons per coulomb. How fast are the electrons moving in terms of the speed of light? What magnetic field is needed here to select those electrons? And then what happens if you crank up this accelerating voltage? So we're going to select the electrons. From energy, the work done on the electrons, E times V, will give us the kinetic energy. So the velocity is rad 2eV over m. V over c, comparing it with the velocity of light, plug in the numbers for V that we just talked about, the proper units, and c. So that's 0.024 c, or 2.4% the speed of light. What's the magnetic field needed? V is E over B, B is E over V, velocity. Plug the numbers in, and we get 0.83 Tesla. Now what happens when we increase that accelerating potential? Well, you know what happens. It does more work on the charge. Work goes up, it enables the kinetic energy to go up. If kinetic energy goes up, that must mean the velocity has gone up. Velocity has gone up, the QVB force goes up, which is the magnetic force. Now, magnetic field is in. Stick your fingers in to the page. Put your thumb to the left because it's the opposite direction for a negative charge. And your palm points where? That's right, down. Just like that.
Wee. Uh-oh. Oh, no. Ow, that hurt.
Yeah, well, get over it.